Hi, in today's video we're going to be talking about types of bond-forming reactions and classes of bond-forming reactions. So we classify these reactions based on the types of bonds that are being made and broken. So for example, a substitution reaction involves a reaction when you're displacing a group that we can simplify as Y, so really any kind of atom or functional group Y, we are replacing this with X, typically on carbon. And so you can look for a substitution reaction, no matter what the mechanism is, by the fact that you've replaced a sigma bond for a new sigma bond. Another type of reaction that we'll look at are elimination reactions. So elimination reactions are when you have two bonds, like a carbon to Z, this could be a hydrogen, it could be lots of other things, and here is a carbon to Y, another functional group or atom. It doesn't matter for this time being what exactly those are. So an elimination reaction involves when two sigma bonds are now transformed into a pi bond or a double bond. The third type of reaction that we're going to cover in this class are addition reactions. So this is when you have a double bond here, and this reacts with another molecule or a set of molecules, like simplified as XY, and both X and Y are added across that double bond. So you look for addition reactions by seeing that a pi bond now becomes two sigma bonds. So an addition reaction is, you can think about that as effectively the opposite of an elimination reaction, two sides of a coin. Finally, the book doesn't talk about this, but there is a fourth class of reactions called rearrangements. We're not going to go through them very often in class. This is an example of a rearrangement that has a name. Most rearrangements have names associated with them. For example, this one is called the Curtius rearrangement, named after a chemist whose last name was Curtius. You will not be asked to do the mechanism, and these are harder to predict. It's really almost any type of bond forming and breaking, which doesn't fall into these other classes of reactions. So let's look again briefly at the two ways that we can break bonds. So the first way we can break bonds is homolysis. So this is when you have a molecule, or rather a bond, X bound to Y, and the bond is highlighted in purple here, and this now becomes two electrons on X and Y. So we will use a single-headed arrow, electron arrow, and that is not a mistake. That single-headed arrow indicates that there is a single electron flowing. And you notice that we draw it from the middle of the bond, breaking in both directions. So that's how we draw arrow pushing mechanisms for what are called radicals. So these are singly occupied molecular orbitals, or in this case, these look more like atomic orbitals because X and Y, you can think about these as atoms, but they can also be whole portions of molecules. This is this is what we think about when we're talking about a bond dissociation energy of a bond. It is the homolytic cleavage. And again, it's homo because each are getting the same number of electrons. The other style of bond cleavage is heterolysis. And so this is when one atom gets all of the electrons and the other atom doesn't get any of them. So you end up with an atom that is often hypovalent, that is lacking a full octet. So in the case of carbon, you can have it both ways, where carbon can homolytically cleave, where in this case this Y would take the electrons with it, and you'd be left with a hypovalent carbon, or a carbocation. So this is a carbon with 6 valence electrons and a formal positive charge. You can also have a scenario where the bond from carbon to some other group, the bond breaks and these electrons wind up on carbon. And in this scenario, you wind up with what's called a carbanion, a carbon with a negative charge. And in this case, a carbanion has a full octet. There are a couple other things to think about in the context of bond making. So you can have the extreme scenario where you have a nucleophile interacting with an electrophilic carbon. So in this case, this carbon is hypovalent, so it has an empty orbital that these electrons can occupy. And from an arrow pushing perspective, we simply draw that these electrons are going to form a bond, and we now form a nucleophile to carbon bond. The other type of bond-forming reaction that we've seen before is when we have a nucleophile and it's interacting with a carbon, and that carbon is actually, it has a full octet. It has all of its valence electrons filled. That means that we're going to have to break a bond as we're making a bond. And so I've signified this Lg, and this is a new idea in our class, and this is called a leaving group. And so leaving groups are either functional groups or portions of molecules that when they break away from a molecule with a negative charge, they are often quite stable. So actually all of our knowledge that we had based on acids and bases and the stability plays into our understanding of what would make a good leaving group. So if we're looking at how this occurs, the nucleophile interacts with the antibonding orbital of the carbon to leaving group. When you push electrons into that antibonding orbital, you're actually now breaking the bond. You're destabilizing the carbon to leaving group bond. The electrons that were in that bond wind up on the leaving group, again because that leaving group is stable with those electrons, and you've formed a new carbon to nucleophile bond. That's all for today, and I look forward to seeing you next time. Thanks.